So this is exercise 6 on page 288, the Gram-Schmidt orthonormalization process. Remember, vectors are orthogonal or perpendicular if their inner product is 0. The length of a vector is just defined to be the square root of the inner product of the vector with itself. And a unit vector is a vector whose length is 1. And given a basis V, we want to construct from that an orthonormal basis. So to do that, the first step is to make sure we understand how to decompose a vector with respect to another vector W into two pieces, the piece parallel to W and a piece perpendicular to W. So the component of a vector parallel to W is given by the inner product of V and W over the length of W squared times W. That's the parallel component. And V minus that, V perp, is the perpendicular. So suppose I have a basis, let's say it's a three-dimensional space, which is what it is in this problem. We have V1, V2, V3. So first I'm going to construct an orthogonal basis. So that's a basis where the vectors are perpendicular to each other, and then divide each vector by its length. Then we can get an orthonormal basis. So first we get an orthogonal basis, and then we simply contract each vector so its length is 1. So imagine here we have V1, which is W1. Here we have V2. I want to find the component of V2 perpendicular to W1. So I'm going to let W2 be the component of V2 perpendicular to W1, which is V2 minus the parallel component, V2 W1 over the length of W1 squared times W1. So this is exactly the component of the vector V2 perpendicular to W1. So if this is V1, which is W1, and this is V2, this is the component, this is the parallel component. This is the component of V2 parallel to W1, and this is the perpendicular component. And then how do I get W3? To get W3, I want to take V3 and subtract from it is the components that are parallel to W1 and the components parallel to W2. So I'm going to take V3 minus V3 W1 over the length of W1 squared times W1 minus V3 W2 over the length of W2 squared W2. So in this problem, problem 6, we have a basis for R3 where V1 is the vector 1, 2, 3. V2 is the vector 2, 3, 1. And V3 is the vector 3, 1, 2. Actually, the first step is to prove these three vectors are a basis. So how do we do that? We say, suppose x1 v1 plus y, or let's say x1 v1 plus x2 v2 plus x3 v3 equals 0. That's the same as saying that the 0 vector is x1 times the vector 1, 2, 3 plus x2 times the vector 2, 3, 1 plus x3 times the vector 3, 1, 2. If we add this up, we get the vector x1 plus 2x2 plus 3x3, 2x1 plus 3x2 plus 1x3, 3x1 plus 1x2 plus 2x3 equals 0. So we're solving 3 equations and 3 unknowns. If you write down the matrix of coefficients of these equations, 1, 2, 3, 2, 3, 1, 3, 1, 2, and we put it in reduced row echelon form, let's see, what do we get? 1, 2, 3, subtract twice the first row from the second row. 2 minus 2 is 0, 3 minus 4 is minus 1, 1 minus 6 is minus 5. Subtract 3 times the first row from the third row. 3 minus 3 is 0, 1 minus 4 is minus 3, 2 minus 6 is minus 4. So let's see. If I add, if I multiply this row by 0 by minus 1, or if I add twice this row to the first row, I get 1, 0, minus 10 plus 3 is minus 7. If I add 3 times this row to this row, I get 0, 0. 15 minus 4 is 11. And if I can continue just to put this in reduced row echelon form, I mean, you can do the steps yourself. I get this matrix. So this set of equations is equivalent to x1 equals 0, x2 equals 0, x3 equals 0. So that's a quick proof that these 3 vectors are linearly independent, and so they form a basis. So how do I get an orthogonal basis from them? So V1 is 1, 2, 3. V2 is 2, 3, 1. V3 is 3, 1, 2. So I let, this is the first step, W1 just be the first vector. W2 be V2 minus the component of V2 in the direction of W1. Right? What is that? V2 is 2, 3, 1. The inner product of V2 and W1, the standard inner product, is 2 plus 6 is 8 plus 3 is 11 over the length of this vector squared. This vector has length squared. 1 plus 4 plus 9 is 14 times the vector W1. So what is this? W2 is 2, 3, 1 minus 11 over 14. 2 times 11 over 14. 3 times 11 over 14. This is 14 minus 11. 3 over 14. See, 3 times 14 is 42, minus 22 is 20 over 14, or 10 over 7. 1 minus 33, 14 minus 33, I think is minus 19 over 14. So this is the vector W2, if I did my arithmetic correctly. This is W1 is V1. W2 is the component of V2 perpendicular to W1. So it's V2 minus the parallel component. The inner product of these 2 vectors is 11. The length of W1 squared is 14. So it's that times the vector W1. So that's 22 minus 11 is 30. Oops. This is 22. Sorry, this is, I did my arithmetic wrong. This is 2. This is 2 is 28 over 14 minus 11 over 14. Right? Let me just do this in 2 steps. So 2 is 28 over 14. 3 is 42 over 14. 1 is 14 over 14. Minus 11 over 14. 22 over 14, 33 over 14. So I get 17 over 14, 20 over 14, minus 19 over 14. So that's the vector W2. And W3 is going to be the vector V3, which is 3, 1, 2. So let me write, this is going to be V3 minus V3W1 over the length of W1 squared times W1 minus V3 inner product with W2 over the length of W2 squared times W2. All right. So there's just a lot of arithmetic here. I'll just set it up and you can do the arithmetic. V3 is 312. The inner product of V3 and W1 is 3 plus 2 is 5 plus 6 is 11 over the length of W1 squared, which is 14 times 1, 2, 3, minus the inner product of V3 and W2. So the inner product of V3 and W2, let me just write it over here. The inner product of V3 and W2 is going to be 3 times 17 over 14 plus 1 times 20 over 14 plus 2 times minus 19 over 14. So that's 51 plus 20 minus 38 over 14. That is, I believe, 71 minus 38 is 33 over 14. Yeah, 33 over 14. So this is minus 33 over 14 divided by the length of W2. What's the length of W2 squared? It's 17 over 14 squared plus 20 over 14 squared plus minus 19 over 14 squared. Right, so you do that calculation, whatever it is, times W2. And that's it. Oh, sorry. So then you have W1, W2, W3. So W1, W2, W3 is an orthogonal basis. The vectors are not orthonormal. But then you can let, for example, E1 be W1 divided by the length of W1, E2 be W2 divided by the length of W2, and E3 be the vector W3 divided by the length of W3. And the answer to the problem will be E1, E2, E3. So, you know, sometimes you have to do some work. And in this case, you have to do a lot of work. But is there any question about the method as opposed to the arithmetic? Let's see if I can get this all on the same page, on the same screenshot. That's pretty close. Right. Any questions about this? Any other problems that I should go over? I'm happy. All I want to do today is answer questions because it's the last official class before the final.
How many questions are going to be on the final?
People always ask that question. I'm never sure why it's of interest. It's, 10, 11, 12, it's comparable to the midterms. Um, it's roughly the same amount of time, so an extra 20 minutes. So, and there'll be extra credits for extra credit. Um, Nothing, significantly different from the midterm exams.
Will there be like a lot of proofs like the last one?
Well, let me take a look at the last one, because let's see. So in the last exam, you had to show if a set of vectors were linearly dependent or independent. The next question was to prove that two vectors were linearly independent, but that's not really a proof. That's just a calculation. There was a problem that really was a proof about problem number 4, number 5. Yeah. So the last test was probably about half proofs. This will be a little bit less than half. But the proofs were really, most of the proofs were basically just like more calculations in linear algebra. They weren't like a serious proof of a theorem. There's only one real theorem, I think, that you were asked to prove. Let me do a couple of exercises on page
Can you do number
351.
4 on page 275?
Page 275.
Yeah, number 4.
Okay. So on page 275, number 4, we have C01 is the vector space of continuous functions on the unit interval. And if you take two functions, the inner product is defined to be just the integral of their product from 0 to 1. So if we take, for example, f of t to be 1 plus 2t, the length of f is defined to be the square root, the length of any vector is the square root of the square of the inner product of the vector with itself. So what is the inner product of the vector with itself? This is the integral from 0 to 1 of f of t times f of t dt, or just f of t squared. That's the integral from 0 to 1 of 1 plus 2t squared dt. That's the integral from 0 to 1 of 1 plus 4t plus 4t squared dt. The integral of 1 is 1. The integral of 4t is 2. The integral of 4t squared is, I think, 4/3. So this is 3 plus 4/3, which I think is, let's see, 3 is like 9 over 3. This is 13 over 3. So the length of this vector f is the square root of 13 over 3, if I did my arithmetic correctly, right? The integral of 1 is 1. The integral of 4t is 2t squared. The integral of 4t squared is 4/3 t cubed. So that's the length of f, for example. And, these are just integrals. If you want to, if g of t is the function e to the t, the inner product of f and g is the integral from 0 to 1, f of t, g of t, dt. That's the integral from 0 to 1 of 1 plus 2t times e to the t dt. That's the integral from 0 to 1 of e to the t plus 2t e to the t dt. So we have to calculate these two integrals. The integral from 0 to 1, the integral of e to the t is just e to the t. Evaluated from 0 to 1 is e to the 1 minus 1. That's what this first integral is. The integral from 0 to 1 of 2t e to the t dt, you have to use integration by parts, or you can at least. This is 2t, this is 2. If this is e to the t, this is e to the t. So this is equal to 2t e to the t evaluated from 0 to 1 minus the integral from 0 to 1 of 2 e to the t dt. So when t is 1, this is 2e. When t is 0, this is 0. Minus 2, and the integral of e to the t we already saw is e minus 1. So 2e minus 2e plus 2, this is 2, if I did this correctly. So the inner product of f and g is this integral, which is this plus this. It's e minus 1 plus 2 is e plus 1. So that's the answer, right? And that's how you set up all the different parts of this problem. You've taken, calculus is certainly a prerequisite for linear algebra, and you need to know calculus. Are there any other parts of this problem that I should do? All right. Let me just pause for 1 second, please. So let me go to page 351. If there were 3 pages in the assignment for today, and I didn't do anything from that yet. So this is to calculate eigenvalues and eigenvectors for some 2x2 matrices. So this is on page 351, number 1. And let's just recall we have a linear operator, a linear transformation from a vector space to itself. And we say that a vector v different from 0 is an eigenvector with eigenvalue lambda if t of v is just the scalar multiple lambda of v. So we consider the operator t, this is in part A, from R2 to R2, defined by the matrix 1, -1, 2, 4. This means t of the vector, let's say xy, is this matrix applied to xy. That's x minus y, 2x plus 4y. And we want to find an eigenvector, right? So this is the linear operator defined by the matrix 1, -1, 2, 4. And we want to know for what vectors x, y, not both 0, is there a lambda number, a scalar, such that this is lambda times xy, which is lambda x, lambda y. So finding eigenvectors and eigenvalues is equivalent to solving the equations x minus y equals lambda x, 2x plus 4y equals lambda y, which is the same as the system of equations x, bring this over to the other side. 1 minus lambda x minus y equals 0, 2x plus 4 minus lambda y equals 0. So we want to try to solve these two equations in two unknowns. And how we solve that is up to us, I guess. Let's see. So we know that this is a homogeneous system of two equations in two unknowns, x and y. And we want to know when there's a solution where x and y are not both 0. So the system has a non-zero solution, x and y, if and only if the determinant of the coefficients is not 0. What are the coefficients of x and y? If we write down the matrix for them, 1 minus lambda, minus 1, 2, 4 minus lambda. And the determinant of this 2x2 matrix is AD minus BC. 1 minus lambda, 4 minus lambda, minus 1 times 2. Let's see, what is that? This is, if I multiply this out, this is lambda squared minus 5 lambda plus 4 plus 2. That's lambda squared minus 5 lambda plus 6. When is that equal to 0? Solve the quadratic. Well, that's easy because this factors. This is lambda minus 2, lambda minus 3. So the eigenvalues for this matrix are lambda equal 2 and lambda equal 3. So for each of these two different values of lambda, we can find a non-zero solution. Let's see. What do these equations become when lambda is 2? If lambda is 2, we get minus x minus y equals 0. 0. 2x plus 2y equals 0, which is just the same as x plus y equals 0 or y equals minus x. So for lambda equal 2, we have the eigenvector v equal to x minus x, or x times 1 minus 1. So for this matrix, for this linear operator, lambda equal 2 is an eigenvalue, and an eigenvector is 1 minus 1, or any scalar multiple of that. What about when lambda equals 3? When lambda equals 3, this first equation is 1 minus 3, is minus 2x minus y equals 0. The second equation is 2x plus y equals 0, which are the same as y equals minus 2x. So a solution is x minus 2x, or x times the vector 1 minus 2. So for the eigenvalue lambda equal 3, an eigenvector is 1 minus 2, or any scalar multiple of that. So this matrix, this linear operator defined by the matrix 1 minus 1, 2, 4, has eigenvalues 2 and 3, and I found the eigenvectors. Okay, is there a question about that? Let's do part B. In part B, we have the matrix 1, 2, minus 1, 4. And this times the vector xy, this is t of xy, is x plus 2y minus x plus 4y. And we want to know, when is there a non-zero solution to this equal to some lambda times xy, or lambda x lambda y, which is the same as the two linear equations, x plus 2y equals lambda x minus x plus 4y equals lambda y. Or bringing all this, everything to the left side of the equation, 1 minus lambda x plus 2y equals 0, minus x plus 4 minus lambda y equals 0. And these equations have a non-zero solution if the determinant of the matrix of coefficients 1 minus lambda 2 minus 1 4 minus lambda, which is 1 minus lambda 4 minus lambda, minus oh, this is almost the same as the previous problem. Not sure why I put this down, but let me just finish it since I have it. Minus 2 is lambda squared minus 5 lambda plus 6, or lambda minus 2 lambda minus 3 equals 0. So we have two eigenvectors, again 2 and 3. Let's see what the corresponding eigenvalues will be. When lambda equals 2, this first equation is minus x plus 2y equals 0, or x equals 2y. Second equation is minus x plus 2y, exactly the same equation. So x equals 2y, so we get 2y, y, or y times the vector 2, 1. So the eigenvector with eigenvalue 2 is 2, 1. Actually, let's just sort of check. If I take 1, 2 minus 1, 4 times the vector 2, 1, I get 4, 2, which is 2 times 2, 1. So this matrix times this vector is 2 times the vector. So this is an eigenvector with eigenvalue 2. When lambda is 3, this is the equation minus 2x plus 2y equals 0. This is, which is the same as minus x plus y equals 0, or x equal y. So we get xx, or x times 1, 1. So this is an eigenvector with eigenvalue 3. Let's check that. 1, 2 minus 1, 4 times 1, 1 is 3, 3, which is 3 times 1, 1. So the matrix times the vector 1, 1 is 3 times the vector 1, 1. So 1, 1 is an eigenvector with eigenvalue 3. Any questions about that? Let's look at C. So still, page 351, number 1, C. We have the matrix 8 minus 6, 5 minus 3. This times the vector xy is 8x minus 6y, 5x minus 3y. And we want to know when is lat equal to lambda x times lambda y for some lambda. All right, so we want to find lambda such that the matrix times the vector is a scalar times the vector. So again, this corresponds to solving 2 equations and 2 unknowns. The equations are 8x minus lambda x, 8 minus lambda x, minus 6y equals 0, 5x minus 3y minus lambda y minus 3 plus lambda y equals 0. And again, a homogeneous system of 2 equations and 2 unknowns has a non-zero solution if and only if the determinant of the matrix of coefficients, 8 minus lambda minus 6, 5 minus 3 plus lambda, which is this times this, 8 minus lambda times minus 3 plus lambda, minus 5 times minus 6 is 0. See, if I multiply this together, I get what? I get minus lambda squared plus 5 lambda plus 24 plus 30 equals 0, which is the same as lambda squared minus plus 5 lambda minus 6 equals 0. We have to solve this. So I'm just solving, now I'm just doing my high school algebra. This equation, I have to solve it, but again, we're lucky this factors. This is lambda plus 6 times lambda minus 1 equals 0. So we have eigenvalues. Lambda equals 6, lambda equal minus 6, and lambda equal 1. If lambda is minus 6, this is the equation 14x minus 6y equals 0. This is the equation 5x. So let me check my arithmetic because something doesn't look quite correct here. 8 minus 6, 5 minus 3.
I think it's plus 6, not minus 6.
Yeah, let me just check. So this is minus 24 plus 6. Huh. Okay, well, unfortunately, it's not very, it's just the same eigenvalues as before. So if that's the case, let's see. minus lambda squared minus 5 lambda. No, this is minus lambda squared minus 5 lambda plus 6. So, no, this was correct. Let me just check this. So this is the same as lambda minus 8, lambda plus 3 plus 30 equals 0, lambda squared minus 5 lambda minus 24, oh, plus 6 equals 0. That's right. So this is lambda plus 2, lambda plus 3 equals 0. So the eigenvalues are minus 2 and minus 3. When lambda is minus 2, this is 10x minus 6y equals 0. This is 5x oops, sorry. When lambda is minus 2, it's 10x minus 6y equals 0. 5x minus y equals 0. So something isn't right here. I need to figure it out. 8x minus 6y, 5x minus 3y, lambda x lambda y. So it's 8 minus lambda times x minus 6y equals 0. 5x minus 3y minus lambda y, or minus 3 plus lambda. So this is 8 minus lambda minus 6, 5 minus 3 plus lambda. The determinant is 8 minus lambda times minus 3 plus lambda, which is lambda minus 8 times lambda plus 3 plus 30. Lambda squared minus 5 lambda plus 6 equals 0. So lambda plus 2, lambda plus 3. So when lambda is minus 2, this is I should be getting the same equation. Lambda squared minus 5 lambda. Yep, minus 5 lambda. Lambda squared minus 5 lambda plus 6. So lambda minus 2, lambda minus 3. So my lambda should be plus 2 and plus 3. 2, 3. When lambda is 2, that's 6x minus 6y. 5 equals 0. 5x minus 5y equals 0. This is all the same as x equal y. So we just get the vector xx, or x times 1, 1. So 1, 1 should be an eigenvector with eigenvalue 2. When lambda is 3, this is 5x minus 6y equals 0. Second equation is exactly the same. So I could take, for example, I could say y is 5, 6x. So I can have x 5, 6 x, or x times the vector 1, 5, 6. I could also have taken 6, 5, but that's fine. Let's just check. So if I take 8 minus 6, 5 minus 3 times the vector 1, 1, I get 8 minus 6, 5 minus 3, which is 2 times 1, 1. So the matrix times this vector is 2 times the vector. So the vector is an eigenvector with eigenvalue 2. I take 8 minus 6, 5 minus 3 times the vector 1, 5, 6. I get 8 minus 5, which is 3. 5 minus 5 halves, which is 5/2, which is exactly 3 times the vector 1, 5/6. So the vector, the matrix times this vector is 3 times that vector. So everything works out okay. Any questions about that? So these are very important problems to know. Let me do a couple more. Let's see. Let's say problem 3, number C. I'm just choosing at random. I have no idea what's going to work out. So the matrix is 3, 4, 2 minus 4. So if you multiply that by a vector xy, you get 3x plus 4y, 2x minus 4y. And we want to know when that gives the vector lambda x lambda y. For some non-zero x and y, or x and y not both 0, and lambda can be 0. So this corresponds to the equations 3x plus 4y equals lambda x, 2x minus 4y equals lambda y. So we're looking at the two equations and two unknowns that are homogeneous. 3 minus lambda x plus 4y equals 0. 2x plus minus 4 minus lambda, so that's minus 4 plus lambda y equals 0. And if you look at the matrix, 3 of coefficients, 3 minus lambda, 4, 2 minus 4 plus lambda, and you take the determinant, that's 3 minus lambda times minus 4 plus lambda minus 4 times 2. This is, let's see, minus 3 minus lambda is lambda minus 3 times lambda plus 4 minus 8. This is lambda squared plus lambda minus 20, which I believe factors into lambda plus 5, lambda minus 4 equals 0. So we have eigenvalues 4 and minus 5. Right? Those are the two values of lambda for which these two equations and two unknowns have a non-zero solution. When lambda is equal to 4, this equation is minus x plus 4y equals 0. And this equation is 2x minus 8y equals 0, which are the same equation. X equals 4y. So an eigenvector is 4y, or y times the vector 4, 1. Let's check. If I take the matrix 3, 4, 2 minus 4 times the vector 4, 1, this is 12 plus 4 is 16. 8 minus 4 is 4. That's 4 times the vector 4, 1. So the matrix times 4, 1 is 4 times 4, 1. So this is an eigenvector with eigenvalue 4. What about lambda equal minus 5? When lambda is minus 5, this is 8x plus 4y equals 0. This is 2x. When lambda is minus 5, this is minus 1 times minus is plus y equals 0. So these are the same equations. Y equals minus 2x. So for any x, this is minus 2x. So this is x times the vector 1 minus 2. So this should be an eigenvector with eigenvalue minus 5. So let's check this. My matrix is 3, 4, 2 minus 4 times the vector 1 minus 2. This is 3 minus 8 is minus 5. 2 plus 8 is 10. And this is exactly minus 5 times the vector 1 minus 2. So 1 minus 2 is an eigenvector with eigenvalue minus 5. Let's see, number 4 looks interesting. So let me do number 4, still on page 352, number 4. So there is a rotation transformation. You take any vector v and you rotate it by an angle alpha. So this is rotation by an angle alpha radians of the vector v. And so R alpha is rotation by alpha radians of a vector in the plane. And this linear transformation has a matrix which is cosine alpha, sine alpha, minus sine alpha, cosine alpha. And since we're looking at eigenvalues and eigenvectors, we can ask for what rotations alpha are there eigenvalues and eigenvectors. So if you think about this a little bit, what is an eigenvector? It's a vector, and when you apply your linear transformation, it just stretches it in the same or in the exact opposite direction. But if you take a vector and you rotate it by an angle alpha, it's going to be in a different direction, except in 2 cases. So we should expect R alpha has no eigenvalue unless there's either no rotation, alpha equals 0, or it's a rotation by pi radians, alpha equal pi. Because eigenvector means you stretch the vector. The vector stays on the same line through the origin. If you rotate by other than 0 radians or pi radians, you won't have an eigenvector. But let's just check. Let's just check doing the kind of algebra we've been doing. So cosine alpha minus sine alpha, cosine alpha, applied to a vector xy is cosine x, cosine alpha times x. So that's the way we normally would write this. That's x cosine alpha minus y sine alpha, x sine alpha plus y cosine alpha. And when is that going to be equal to lambda x lambda y? When do we have an eigenvector with eigenvalue lambda? So this corresponds to the equations cosine alpha minus lambda x minus sine alpha times y equals 0. Sine alpha times x plus cosine alpha minus lambda y equals 0. Right? This is x cosine alpha minus lambda x is cosine alpha minus lambda times x minus sine alpha times y, and so on. And the corresponding matrix of coefficients is cosine alpha minus lambda minus sine alpha, cosine alpha minus lambda. And the determinant of this is cosine alpha minus lambda squared minus sine alpha times sine alpha plus sine alpha squared. This is cosine squared alpha minus 2 lambda cosine alpha plus lambda squared plus sine squared alpha. Cosine squared plus sine squared is 1. So this is lambda squared minus 2 cosine alpha times lambda plus 1. And we want to know for what lambda is this equal to 0. So we have to use the quadratic formula. Lambda is minus b plus or minus the square root of b squared minus 4ac over 2. That's equal to cosine alpha plus or minus the square root. I can factor out the 4, take the square root, cancel the 2. Cosine squared alpha minus 1. This is negative, and so there's no solution unless cosine squared alpha equals 1. So cosine squared alpha is between 0 and 1. Unless it's 1, this is going to be negative, so there won't be any solution. And when is cosine squared of alpha equal to 1? If and only if alpha is equal to 0 or pi. So the only time a rotation as an eigenvector or an eigenvalue is when it's a rotation by either 0 radians or pi radians. So that's kind of nice to see how the algebra and the geometry fit together perfectly. Any questions about any of this? Any other problems you would like me to do, either from this homework or from anything that we've done since August?
Will you be giving out a review sheet or?
So, if you, if you look at the assignments, you'll see there's only one thing new that we've done since the second midterm, which is what I was going over today in homework 13. So you already have a review sheet for the first midterm, a review sheet for the second midterm, and this homework, and that altogether is a review sheet for the course. So you don't really need any other review sheet because everything is covered on those review sheets. But I will be scheduling, as always, a lot of Zoom office hours. So if you have questions about anything on the homeworks, on the review sheets, on the exams, I encourage you to log into a Zoom session and ask questions. They are usually underutilized, the Zoom problem sessions. So if you log in and have a problem that you would like me to do or something you would like me to explain, I will certainly get to it. You won't have to wait very long.
So most of the final exam is going to be about like eigenvectors and eigenvalues and the Gram-Schmidt orthonormalization process?
No, very little. The final exam is comprehensive. It covers the whole course. So the Gram-Schmidt, so inner products and eigenvectors and eigenvalues will be on the exam, but maybe 2 questions out of 12. I mean, most of the exam, because that was a small part of the course. The final exam covers everything, starting with solving linear equations and so forth. It's not an exam on just what we did since the second midterm. It's an exam on the whole course in linear algebra. All right. If there's nothing else, then we can stop for the morning. The exam is, I believe, a week from today. And I'll be having 3 or 4 or 5 problem sessions before the exam, so you can log on again at any time and ask questions.
Are you able to post questions from midterm 2 and midterm 1?
I'm sorry, say that again, please.
So are you able to post questions for midterm 2 and midterm 1?
You mean the actual exams?
Yeah.
Oh, if they're not on the website already, I'll put them on right away.
Okay, thanks.
Yeah, but I assume everyone has the midterms because I emailed them to you, but I'll put them on just so you have them. No, thank you for asking. I will do that right away.
You said you emailed us the midterms?
Well, I mean, how'd you get the midterm?
We didn't get it.
We didn't get
Oh,
it.
I'm sorry. No, sorry. I was thinking it was still the summer and in the summer session, everything is on Zoom, including the exams. Yeah, I will put I will post them right away. I usually try and do that after the exam, but no one asked and I forgot. I'll do that right away, within a couple minutes after I log off. And if you have other requests of that sort, just email me and I try to answer emails fairly promptly. Anything else? Okay. See you next Monday and maybe see you in Zoom. All right. Bye all.